back to another example here. This time we have n equals 1 to infinity 1 over n to the 4/3. And this is what's called a p-series, and they take this form. Okay, and depending on what p is, we'll have some different things happening. So first of all, notice it meets all the conditions. F of x is positive, it's continuous, and it's also decreasing. So you be sure to check those things before you begin this. Now let's go ahead and let's do that. So positive, continuous, and decreasing, all three. I'm going to integrate with this. Oh, sorry, that should be an x. Whoops. Okay. All right, here we are. Okay, so that is an x in there. Okay, now this becomes x to the negative third, the negative 3 out here, from 1 to infinity. And we're going to have to evaluate that. So b goes to infinity. Negative 3b to negative 1/3 plus 3, period. Now that it's important, watch the signs here, it's a negative. So this is the limit. B goes to infinity to negative 3 over b to the 1/3 plus a 3. Now that heads to infinity, forcing this fraction to 0, which means we get a 3. So it's convergent. Convergent integral, therefore convergent series. Now, if we change that p on the next problem, this is problem, same problem but h, and we have this form. This is 8/9. Okay, 1 over n to the 8/9. And it meets the conditions, it's positive, continuous, and decreasing. So if we integrate it, we've got x to negative 8 over 9. And that will become, and of course, remember, we're going from 1 to infinity. I'm getting a little sloppy here. I'm trying to rush this in. Can't do this as quickly here. So I'm trying to keep it a little more streamlined. Okay, so we have an x to the negative 1/9. Sorry, positive 1/9. And then times a 9. Okay, so if we added a 1 to this, become 1/9. 5 by 1/9 is 9. And we're going to go from 1 to b, and with the idea being that we're going to let b go to infinity. So this is the limit. B goes to infinity. 9 b to the 1/9 minus 9. Now, even though this doesn't go to infinity very quickly, it's only 1/9 power. It does go to infinity, so this goes to infinity, and we have divergence. Divergence. So divergent series. Now the critical number here is, you might be wondering, this was 4/3, that's bigger than 1. This is 8/9, that's less than 1. Somehow between those two, you notice the big difference, convergence, divergence. The key number is p equals 1. That's where everything goes wrong, right? At P equals 1, the general result is in the next theorem there. We have our general result. I'm gonna erase this here for now and just get back in here. General result. Here we have, for this form, 1 over n to the p. Again, it's called the p-series. It will diverge if p is less than or equal to 1. And of course, we're looking at only positive values of p. And it will converge if p is greater than 1. As a general rule. So now, whenever we see this form, so-called, it's called a p-series, we can make this assumption. We don't have to go through the integral test anymore. If we can identify it as a p-series, okay. Now, just a little note here. If you see something like this, let's say you've got 1 over n squared plus a 1. This is not a p-series. Now, we'll be able to, with the aid of a couple other tests, we will be able to handle this. It behaves similar to a p-series, but you couldn't cite the p-series test only to say what happens to this series. So we got to be careful with that. It's not a p-series. We have to view it as a different type of series, possibly do a comparison or something. We'll see later on. We'll have more tools for that, but that's not a p-series. It has to have this form to be a p-series. Okay.